Internal combustion engines, there are so many parts that move, auxiliary parts to control the engine, like the valve train and things like this. The wave disk engine has only one rotating disk, and there is basically no friction between a solid part and another solid part, hence we have less frictional losses in the wave disk engine from the get-go.
Some engines look strange, but this one might be the strangest we have ever talked about on this channel. It throws away pistons, throws away rotors, and replaces them with something that sounds more like a physics experiment than a working machine. This is the wave disk engine, a device that uses shock waves spinning inside a disk to compress and burn fuel. It feels like something drawn on the corner of a chalkboard by a tired professor, yet it was built, tested, and proven to work. Today, we are going deep into how this odd engine works and why it mattered. Now first, like always, be sure to hit the like button down below. It helps us out tremendously with the reach of this video. Thank you. A new kind of combustion. In a normal piston engine, air and fuel mix, and the piston moves upward to compress the charge. A Wankel engine uses a triangular rotor that rotates inside a housing to do the same job. The wave disk engine rejects both ideas entirely. Instead, imagine a flat spinning disk with many narrow channels carved into its surface, spreading outward from the center like spokes. As the disk rotates, these channels line up with openings in the housing. Each alignment allows air to enter, fuel to mix, or exhaust to exit. But the real magic happens inside the channels. When fresh air enters one of these passages, the sudden rush creates a pressure wave. As the channel continues to rotate, this wave reflects off the closed end and meets incoming gas. This reflection creates a natural compression effect. It is not slow like a piston moving upward. It is instant. It happens in microseconds. The gas is squeezed tightly by the shockwave itself. This approach comes from a technology called the wave rotor, a pressure exchanger studied for use in advanced turbines. Engineers realized that pressure waves can do the job of compression far faster than moving parts can. That idea became the foundation of the wave disk engine. Fuel is injected into this rapidly compressed air. Combustion begins almost immediately. The burned gas then shoots out through an exhaust port that appears as the disk continues to spin. Each channel fires many times every second. With dozens of channels around the disk, the engine produces a steady flow of power. It feels less like a mechanical engine and more like a rhythmic drum of controlled explosions guided by physics rather than metal parts. The science behind the waves. Pressure waves are powerful but demanding. A tiny shift in timing can destroy the entire cycle. If the disk rotates too slowly, the wave may collapse early. If it rotates too fast, the wave may not form correctly. The team at Michigan State University, led by Dr. Norbert Muller, spent years modeling these relationships. They had to calculate the exact length and shape of each channel. They had to match disk speed to the natural timing of the pressure waves. They had to design an opening sequence that would allow air to enter at the right moment, fuel to ignite at the perfect point, and exhaust to exit without interfering with the next wave. They also needed to avoid backflow. Backflow happens when a pressure wave bounces in the wrong direction and sends burned gas back into the intake. That would ruin the cycle. Through countless simulations and experiments, they discovered patterns that allowed shockwaves to form and compress the incoming gas with surprising precision. When this worked, the results were impressive. The engine created high compression levels without pistons, without valves, and without a crankshaft. Because the compression happened so quickly, almost no heat escaped into the walls. Heat loss is one of the biggest efficiency killers in engines. Slow compression means more time for heat to leak. Rapid compression traps heat and uses it for combustion. That is why wave disk prototypes reached thermal efficiency levels close to 60%. That number is huge. It is nearly double the efficiency of many gasoline engines on the road today. It even rivals fuel cells, and it did all this with almost no moving parts. It proved that gas dynamics alone could replace some of the most complex engine design mechanisms. It challenged the idea that pistons were essential. It showed that combustion could happen in a cleaner, faster, sleeker way. Why this engine could have changed everything. The wave disk engine was not just efficient, it was compact. One prototype, intended for hybrid cars, was about 20% the size and weight of a similar piston engine. Think of an engine smaller than a briefcase, weighing only a handful of kilograms, yet strong enough to power a generator for an electric drivetrain. That mattered because the engine was designed as a range extender. Instead of driving the wheels, it would spin at a constant speed to generate electricity. Most small engines perform poorly at partial load. They burn fuel inefficiently when you ask for only a little power. The wave disk engine avoided this weakness entirely. It could run at its most efficient point all the time. That meant cleaner operation. Some estimates suggested it could reduce carbon dioxide emissions by as much as 90% compared to a typical gasoline engine used for the same job. Its exhaust system also opened interesting possibilities. Because the gases are left in pulses, engineers explored adding a small turbine to capture even more energy from those bursts. That would make the engine act almost like a hybrid between a piston engine and a tiny jet engine. And the engine was fuel flexible. It could run on petrol, diesel, ethanol, or hydrogen. Hydrogen was especially interesting because its fast burn speed fit perfectly with the quick pressure waves. This made the engine a strong candidate for future clean hybrid systems or small drones where weight and efficiency matter more than raw power. It was small, simple, efficient, and surprisingly powerful for its size. It had the potential to change how we think about small power systems in both cars and compact flying machines. The challenges that stopped its success. Even with all its advantages, the wave disk engine faced problems that were hard to solve. First, there was manufacturing. The channels inside the disk had to be shaped with extreme accuracy. If a single channel was slightly off, the shock waves would not behave as the models predicted. Machining such fine structures at scale would have been expensive and difficult. Cooling was also a major concern. The disk spun at high speeds and dealt with rapid bursts of heat. The housing needed to stay at tight tolerances even as temperatures changed. Too much expansion could ruin the alignment of the ports. Lubrication was another puzzle. Without pistons splashing oil, the engine needed a new way to keep bearings and seals working under high load. All these engineering challenges added layers of cost and complexity. And then came the automotive world shift. Around the time this engine was being developed, the industry turned strongly toward full battery electric vehicles. Funding for unusual combustion designs dropped. Companies were less interested in supporting risky new engines, even efficient ones. As a result, the wave disk engine never moved beyond the prototype stage. It proved the concept worked, but it never became a product. It now sits in the category of ideas that could have been revolutionary, but arrived at a moment when the world was looking elsewhere. Yet the idea still feels relevant today, especially as people continue to struggle with range anxiety and charging challenges. A future possibility, not a closed chapter. The wave disk engine may not be on the road today, but the idea behind it is far from dead. It remains one of the most promising designs for compact power generation. Small drones, portable generators, and hybrid systems could all benefit from a tiny, efficient engine that burns clean fuel and has very few moving parts. Hydrogen-powered versions could fit well into a low-carbon future. And as battery technology reaches its limits for certain uses, engines like this may return to the spotlight. The wave disk engine proves that combustion still has room for innovation. It reminds us that new ideas can appear even in fields we think are fully explored. It also shows that physics can replace complex machinery when engineers are willing to trust the science. Whether it returns or not, the wave disk stands as a bold example of what happens when someone challenges long-standing assumptions. It is strange, elegant, and full of potential, and it might still inspire the next generation of hybrid power systems. It is a wave disk engine, a machine built on pressure waves, simple geometry, and clever timing rather than pistons and valves. It could have changed the future of hybrid engines, and it still might if interest returns. Tell me what you think in the comments. Did this technology deserve more support? Was it ahead of its time? If you know additional research or updates, share them below. And if you enjoyed this deep dive, check out the channel's other videos. Thanks for watching, and I will see you in the next one. Cheers! Always be sure to hit the like button down below. It helps us out tremendously with the reach of this video. Thank you.